Hi, good morning. We started at 10 afternoon session yesterday. Some of this is probably very straightforward. That's
तो आप बोल दीजिए ना पूछ लिया वो बोली मैं आपको भी बोलूँगा कि दूसरों को आप ऐसे कोई और आएगा तो उनको बोलना उनको भी मैंने यही बातें प्रॉब्लम हो जाएगी
Hi, good morning. How are you? What time were we supposed to start? Third. What time were we supposed to start? And what? Oh, not really.
but they all are rat snake
Sorry?
they are rat snake
Rattlesnake. So not one.
rat snake so they are not venomous
They're not one. But still,
yeah we don't know whether they are venomous or not if it is very long means it is most probably it is rat snake
and they're not.
size of rat snake will be very
They're not one.
they are friend of farmers
Friend of ours.
we are staying in their home they are not staying in our home
I'm leaving later. My parents live in I grew up in Vijayawada. Did you have strong background in my mom? classical. Oh, I see. Not, if you are not listening to instruction, now we are going. What about you? Did you have some background? It just sounded peaceful. What about you? Did you have machine learning? Okay. Okay. Fair enough. What about you? You have some background. How many of you know reinforcement learning? Don't have, right? You know it. You use it. I course on reinforcement learning. Oh, the same course has something. So I'm going to cover regression. I'm sure you all know what is regression. And then we'll do some Python exercises. Yesterday, then we'll do reinforcement learning. I'm going to combine reinforcement learning with some basic interaction and resources. It's a set of 5 courses over many, many lectures. Obviously, part of the just scratch the surface, introduce what the deeper, and I'm again a Python exercise. Once that is done, we will look at reinforcement learning. I've all spent about an hour on reinforcement learning. It seems to me that some of you have some basic introduction to reinforcement learning. Reinforcement learning, you can take that out of this, right? But we only have an hour, hour and a half. Again, we're just scratch the surface. But I will also tell you a little bit about some of my research into reinforcement and different versions. Once that's done, I'm hoping to wrap these 2 topics up in the morning by when we come back. Somebody asked me to talk about attention transformers. Has anyone here studied it's fascinating that the way these models function. We don't fully understand what's inside these models. There are certain things that are intuitive, the way they put these models, different neural networks together. It's intuitive, but mathematically, I don't think anyone really understands how this works. But they work, right? So yesterday evening, I don't have slides on that topic. So I teach a course on advanced machine learning. My colleague and co-teacher, my colleague Matthew, he teaches the portion on how that. So I never really studied that topic with depth, although I knew roughly what was happening. So I don't have slides. So yesterday evening I decided to create some slides on large language models. There are a couple of really nice resources online explaining how these models work. So 5 hours, 6 hours, how many slides can I create? I thought I could use Claude. Have you ever used Claude? You've used ChatGPT. ChatGPT is the large language model built by OpenAI. Claude is another large language model built by Anthropic. Anthropic is an example. Claude is basically similar to that. And I had better experience with Claude in coding. So I asked it to use a couple of online resources and write LaTeX code, LaTeX code to prepare 25 slides or something like that. It did a pretty good job. I'm not going to use those slides today because some figures are not much it uses. How many of you use LaTeX? Yeah, if you're not familiar with it and you want to write scientific documents, LaTeX is a fantastic software. You have to code. Now you don't have to code. It's Claude or Chat. You write your code. Right? It's a different world. I can't believe it. I spent so much time as a kid including drawing pictures using a package called Pix. I like LaTeX because equations and text everything looks really sharp on screen. A lot of my slides were also if you don't know LaTeX and you're in the business of writing scientific documents, learn LaTeX. With these language models, you probably don't even need to learn LaTeX, but they'll write it for you. You just have to tell them what to write in LaTeX documents. All right, so let's get started then. We'll start with regression today. Are there any questions from anything we did so far over the last 3-4 days? No? Okay. So, as I mentioned, I decided not to use Claude-generated slides for attention and transformers. Instead, I found there's one guy. I think his name is Amar Jelama. I think he has really nice visuals that explain how large language models work. Okay, so I'm going to give you. I'll tell you what those websites are. You can take a look at those. But in the lecture later this afternoon, we can go through some of those visuals, and I'll explain how these models work and what is self-attention or attention, and what transformers are. So that'll be the last topic we're going to cover today, and later Professor Jayaram from IIT Rupar, he's going to cover, I believe, Bayesian networks. Okay. So I'm covering all the basics of machine learning. Jayaram is going to cover some very advanced topics. And you've also seen a really nice presentation by Mithun, I think on Tuesday or Wednesday, on deep neural networks. So my presentations are, I'm only scratching the surface. I'm not really going into the depths of all the math. That would take significant amount of effort on all of our part if we have to understand all the math. We don't really have the time to do that. But my hope is that by showing you various problems that you can solve in machine learning, using machine learning, my hope is that you can take those ideas, build on those, learn more from other sources, and use these ideas in your research. All right. So far, we've looked at clustering and classification as two main machine learning problems, right? And we've also looked at a few algorithms to solve clustering and classification problems. Okay.
we're going to focus on regression today. And regression is a supervised learning concept because in regression, just like in classification, you have inputs or features, and you also have labels or outputs. The difference between classification and regression is that in classification, in classification, you have inputs X and outputs Y, where these are classes or categorical variables. Okay. On the other hand, in regression, you have the same inputs and outputs, but your Y's are no longer categorical variables, they are real continuous variables. Sorry. So that's the primary difference between classification and regression. They're both supervised learning approaches. These are both supervised learning. Okay. So we're going to define the regression problem, then we'll look at linear regression, non-parametric regression. How many of you have used Gaussian processes here? Have you used Gaussian processes in building models? Those are nonlinear models that are widely used in a number of engineering applications. So we're going to look at Gaussian processes under non-parametric regression. Okay, so what is the regression problem? We have some inputs, xi's, and continuous outputs, yi's. We want to construct a model or a mapping between these inputs and outputs. So we have some x's that generate y's, and we assume that there is some unknown function between them that maps these x's to y's. We want to estimate this. Now, y's are not categorical. If y's are categorical, then you have the classification problem. Because what you assume that y's are not categorical, we have the regression problem. Okay. Now, once we have this function f, for any new xi, we want to be able to use this function to generate a new output or a predicted output. There are different ways in which you can build this function. You can have a linear function. You can have a nonlinear function. Or you can have a non-parametric function. Okay. Now on the screen you see. Sorry, can you? I didn't realize you're not seeing my slides. Can you put my slides on, please? Sorry, is there something I? Oh, yeah. Okay, that makes sense. Okay, thank you. Okay, so if you have a linear model, the relationship between x and y is linear. You often add some noise to that relationship to account for uncertainty in the data. And then the second equation illustrates a nonlinear mapping between xi and yi. Third one is a parametric model. You don't have, sorry, non-parametric model. In a non-parametric model, you don't have any parameters. The non-parametric model simply depends on the data that you have. Okay, so you, for instance, Gaussian processes are a non-parametric model. The model complexity increases from linear to nonlinear to non-parametric model. If you have a linear model, it's a simple model, easy to build, and often linear models are also interpretable. There are different ways of solving these regression models. You can solve them through optimization. For instance, least squares problem, you can solve it through optimization. You can also bring in Bayesian or statistical perspectives. For instance, you can solve regression problems using maximum likelihood or maximum a posteriori estimation. And linear regression, and in fact, all of those other regression problems can be formulated as either least squares problems or maximum likelihood problems or maximum a posteriori problems. Do you all know what maximum likelihood is? Maximum likelihood estimation. Have you heard of maximum likelihood estimation? Some of you are nodding yes. Maximum likelihood estimation, the idea is you try to maximize the probability of likelihood of having seen this particular combination of data. Okay, X, Y. Now there is a certain probability. I'm doing a lot of hand waving here. There is a certain probability that you've seen this data given a theta. Theta is your parameter vector. For every theta, you have a certain probability of having seen the data that you've accumulated. Now what you want to do is find the theta that maximizes the probability of having seen the data that you have collected. That's what's called maximum likelihood estimation. Maximum likelihood estimation is a very important concept that you should all know. In fact, standard least squares, it turns out, is also a maximum. A standard least square solution is also a maximum likelihood solution to regression problems. Maximum likelihood is important because when you estimate a set of parameters using maximum likelihood approach, the variance on those parameters is going to be the best that is possible. Right? There's something called Kramer-Rao lower bound that guarantees that when you estimate parameters using maximum likelihood approach, the variance on the estimated parameters is as small as possible. It actually meets the Kramer-Rao lower bound. I'm not going to cover maximum likelihood estimation, but the intuitive idea that I gave you there is what maximum likelihood estimation is. If you have you used Kalman filters or any estimation algorithms? They all indirectly use some version or variant of maximum likelihood estimation. So there are different ways or different perspectives through which you can solve these regression problems: mathematical, statistical, Bayesian, etc. In statistical, you have frequentist methods and Bayesian methods. I'm not going to cover everything, but I want you to be aware of different approaches to regression. Okay, let's go through linear regression very quickly. You're probably wondering if you have deep learning, it's going to solve all sorts of problems. You can approximate different types of functions. Why do you need linear regression? We still prefer linear regression in certain problems for a few reasons. One, their linear regression models are, they're fundamental, they're very powerful, they're easy to build, they're interpretable, meaning you can clearly understand how different variables, different features in the data are correlated with your outputs, right? It's very, very easy to interpret a linear model. And also, there are a vast number of problems out there where linear models work very well in practice, okay? And there are many industrial applications as well, data analysis, for instance, PCA, in process identification, ARX, ARMA. Do you know what ARX models are? Autoregressive, exogenous models, autoregressive moving average models, etc. And there are many other. PLS is partial least squares, linear model predictive control. There are many areas where linear regression plays a very important role. Okay, so that's why, despite access to tools like deep learning, we're still interested in linear regression. Okay, so let's go through this. I'm sure many of you are familiar with this, but I'm going to build on this linear regression, and then we'll do a little bit of nonlinear regression, and then Gaussian processes. I think this is all in a build-up to introduce you to Gaussian processes. Gaussian processes are a very important modeling tool in the modern context. So let's assume we have a data set of n samples for I equal to 1 to n, and each with a set of dx features or process variables. Okay, so we have n samples and dx features. xji is the ith sample of the jth feature, and the corresponding output. I'm assuming there's only a single output, but it doesn't have to be a single output. You can have multiple inputs, multiple outputs. I'm assuming there's a single output. It's yi. Now, regression problem. In regression, we write the output y hat I. Hat denotes that it's a model. It's not the true measured value. Y hat I is a linear combination of ith samples of all the features. Okay. W1 to Wt are some unknown scalar weights. Now you can write that in matrix form, as shown here, W transpose times Xi. Right. Wj are the regression coefficients. And in vector notation, when you put all your samples together, then you have y hat equal to x times w. Okay. So this is something that I'm sure you're all very, very familiar with. Okay. Then the least squares objective is to minimize the quadratic error between W transpose Xi and the corresponding measured variable or measured output yi. Right. And you square it, that's the quadratic term, sum it over all samples, that gives you this expression over here. This is a 2-norm, xw minus y in vector format, xw minus y, 2-norm of that, whole square. Okay. Now, fw is the least squares loss. You want to minimize that least squares loss in order to find the best model. Now, there are different ways in which you can minimize this loss. For instance, by setting the gradient to 0, which yields an analytical solution, x transpose x inverse times x transpose y. This term is often referred to as pseudo-inverse of x. Now, it turns out that if your noise is Gaussian in the linear model, this estimate of W is also the maximum likelihood estimate. Okay. In other words, this estimate of W maximizes the probability of seeing in an experiment X and Y, the data that you've collected. So when you do it, you can conduct multiple experiments. Now, every time you conduct an experiment, you generate a different data set because there is some noise in the data. Right? In maximum likelihood, the question you're asking is, for what value of W is the probability of seeing the data that I have seen through my experiment maximum? Okay. So that's maximum likelihood estimate. Sorry, I don't think we have the time to go through all the math, but intuitively, that's what it is. So you can, for every value of theta, or W in this case, the probability of generating a certain data is fixed. If you have a linear model with Gaussian noise, if for every value of theta, let me just probably write it in for a simple model here. So if I have y equal to alpha x plus some noise, so every time I collect a sample or conduct an experiment, I generate different values of y for the same value of x. Even if I fix my x is something that we have control over. Typically, this is an input. Therefore, we have control over it. For a fixed x, for the same x, I will generate different values of y. Right? Okay. So if this is Gaussian, let's suppose we do an experiment, we fix x, this is Gaussian, and with zero mean, then y is also going to be Gaussian with a certain mean, that is alpha, and let's say x star, the value that you chose for x. Okay? Now we're trying to, in least squares, we're trying to estimate this alpha. Now I can choose an alpha that puts this alpha x star somewhere over here. This is, after many experiments, this is the distribution I've seen for y. But I can choose different alphas. I can choose an alpha here, alpha x star that places me here. I can choose an alpha x star that places me here. I can choose many different values of alpha. In maximum likelihood estimation, what you do is you choose an alpha such that alpha x star gives you the maximum probability of seeing the data that you have seen. Okay. So that's what maximum likelihood estimation is. Very, very intuitive. I mean, you can write the probabilities. So you can write the probability of y given x and theta, and then you want to maximize this with respect to theta. That's what gives you maximum likelihood estimation. Now, in the case of least squares, this solution is also the maximum likelihood estimate. And as I mentioned earlier, the beauty of maximum likelihood estimation is that when you use that approach, the variance on in this case the alpha or the W over there, the variance on W is minimized. That's an amazing property to have when you build models, right? When you build models, you want to have variance that is as small as possible. And it turns out that if you use this maximum likelihood approach, variance is automatically the least that is possible. In fact, no matter what algorithm you use for estimates, the minimum variance that you can achieve is called Kramer-Rao lower bound. Kramer-Rao lower bound. So Kramer-Rao lower bound gives you the minimum possible variance on estimates. And you achieve that minimum when you use maximum likelihood estimation. I'm sure you've all seen a picture like this when you're doing linear regression. You're trying to find this linear, this hyperplane such that the sum of quadratic errors between the data points and their projections onto this line is minimized. Okay, so we start with linear regression. There are many good reasons for using linear models. But then there are also problems where linear models would not give you the performance that you need. There are many nonlinear systems out there, and you want to, if you want to model them, then you have to have more complex models. That takes us to nonlinear regression. There are many different ways in which you can do nonlinear regression. I'm just going to show you one approach here. Nonlinear regression often increases the model complexity. If your target variable is a nonlinear function of features, we can typically change the basis to include polynomials of a higher order. Now, in this case, we have, in the previous case, we just added the linear term. Here I've added a quadratic term. This is an example with two features. So you have those two features appear with nonlinear terms, and then those two same features appear with two nonlinear quadratic terms. The previous linear regression problem had a dimension of 2. Now, after adding the y-intercept, we had dimension 3. And finally, after including these quadratic terms, we now have a dimension of 5. Right? So your X matrix now has a dimension of 5. Now, in the nonlinear case, we have to replace the X in the linear case with some function of X. This X, the regressor, it's going to have ones to account for the beta, and then x1 i's, and then x2 i's, then it will have x1 I squared, and so on. So different. In the previous case, we had x1 and x2, two features. Now, with the nonlinear case, you have ones that account for the beta, the constant, and then you have x1, x2, x1 square, x2 square. Okay, so that's your phi x. Okay. Okay, now that we have quadratic terms, we will be able to fit data, like the one shown here. You can have a curve. We can have a quadratic curve to pass through the data. One quick thing. Do you know how the variance of least squares parameters varies as a function of number of parameters and the data? Okay, so let me make it a bit more clear. In the previous case, we estimated W. W was, I think, X transpose X inverse times X transpose Y. This was the estimate of W, this for least squares. My question is, this is very important. I think you should have some intuitive understanding of this. What is variance of W? There is a formal way of estimating it. I think it's proportional to X transpose X, the variance, or some function of it. But how does it vary with the number of parameters? I don't remember what I used for number of parameters, but let's say number of parameters is n. Is that my phone? Sorry, I have a phone and I don't. Number of parameters. Capital N is number of data points. So my question to you is, how does this variance, how is it related to these two? N by n, correct. Yeah, I think that's very important. No matter what estimation problem you're solving, it's good to keep this in mind. it's proportional to n over n, I think, times x transpose x, x transpose x, I think, or some variant of that, roughly. So what this means is if you increase the complexity of the model by increasing n, then you will, your variance of the model increases. On the other hand, if you increase the amount of data you have, then the variance is going to decrease. The more data, the better. Less parameters, the better it is for the variance. That doesn't mean you'll have a good model, because for a good model, you have to have better error, overall error, mean squared error. Right? And mean squared error depends not just on variance errors, but also on the bias errors. All right. So using the polynomial basis, it results in lower degree polynomials being nested within higher degree polynomials. As the degree of general polynomial basis increases, the model becomes more sensitive to the training data and therefore provides lower training errors. So you can keep increasing the order of your polynomial, then your errors are going to be lower, but your bias is likely to bias is likely to get lower. Your variance is likely to increase. If you remember, yesterday or the day before, I showed you a bias variance trade-off curve. With these models, you want to keep that trade-off curve in mind. You want to find the right balance between bias and variance errors. Sometimes it makes a lot of sense to trade variance for bias, or the other way around, and achieve a better total mean squared error. Okay, in the example here, you'll see a plot for the same data set with a power of 1, a power of 3, 6, 9, 12, and 15. And by the time you increase the highest order power to 15, you notice that your model is now trying to capture the noise in the data, which is not good. Right? So that's overfitting. So you have to find the right balance between this and that over there. So that's a linear straight line. Doesn't fit the data all that well. This one probably gives you a really good error, but then you see that the model is trying to capture noise, which is not good. You want to avoid overfitting. Okay, so how do we avoid overfitting? We do that using what is called regularization. There are two different ways of performing regularization, L1 and L2 regularization. I'm only going to cover regularization. There are other ways of avoiding overfitting, cross-validation, and dropouts. Okay, so what is, I asked you yesterday, I think, about regularization. It appeared to me that not many of you knew what regularization is. This objective here, this shows what regularization is. In the original version of least squares, we just had this, right? So we're trying to minimize this function. Okay. Now in the regularized version, what you do is, in addition to the model error, you have the weighted 2 norm of the parameters added to the objective function. Okay? So now you're not only minimizing the errors, but you also don't want W, the 2 norm of this W, to be very large, right? So you're trying to reduce that. Typically, you add a term lambda to this W. That lambda is your regularization parameter, regularization tuning parameters. Okay, so what does it do? Now the solution to this least squares problem, let me see if I have it here. If not, I'll write it down. Oh, yeah, it's here. So in the previous case, the solution lambda was 0 when we did least squares without regularization. Lambda was 0, x transpose x inverse times x transpose y gave you an estimate of W. Right? But when lambda is 0, and if x transpose x is not invertible, or it is poorly conditioned, then you will end up with a significant variance on W. So if you can't invert your matrix, your regressor matrix, then you can't estimate W, right? So typically when we say we can't invert the regressor matrix, what we mean is some eigenvalues of the matrix are so close to 0 that when you invert, it sort of blows up, right? And that's not good. You have really high variance in those situations where x transpose x is not invertible. But you can make it invertible by adding this lambda I. If you add this small lambda, what's going to happen is x transpose x, because of lambda, is going to be invertible. Okay. Now that it's invertible, the variance on W will be smaller. Okay. However, because of the introduction of lambda, the bias errors increase on W. So it's this trade-off between bias and variance. Okay. So if lambda is 0, you can have large variance depending on how good your data are. But as you increase lambda, you're trying to increase bias and reduce variance. Variance is going to dramatically reduce. And the advantage is by introducing lambda, you'll reduce variance significantly. You might increase bias a little bit, but the total mean squared error when you add variance and bias is likely going to be smaller. And that's why we use the regularized least squares. So if you have data that are not informative enough, there's not enough information in them, and you're not able to invert these matrices, then you can choose a regularization parameter. Okay. Now, if you're using Python or some of these standard functions, they often have a feature to let you pick a regularization parameter. Yeah. That's the reason we went. That's the impact of the lambda, right? It also helps you. I'm going to show you something called lasso. It's a different form of regularization. So it allows you to have a W that is that's how do I put it? You don't want a W that is let's say that has some really small weights and some really large weights. It doesn't. I don't want to use the word smooth, but let me say the W is going to be nicer if you use regularization, or if you don't use regularization, and if your matrix x transpose x is not invertible, okay, then because it's not invertible, it's quite possible that the variance. Not quite possible. The variance on W is going to be very large. Okay, so let's take. Okay, so let me see if I can explain this better. So what do we mean by variance on W? And I'll give you some examples to sort of drive home the point that I'm trying to make here. So what is? Let's say we have a W with 2 elements in it, okay? And what does variance mean? Every time you generate your data, you get a different W, right? So that's the variance in W. Now let's say I estimate W the first time. I get 0.1 and 10, okay? The next time I estimate it, it's 0.5 and 100. And the third time I estimate, it's probably something like that. There's a lot of variance in these elements. And that variance comes from the fact that you're not able to invert X transpose X. Okay, so your covariance, it's proportional to X transpose X. Right? It's really large. The variance is very large. Therefore, every time you do it, you get a really widely different W's. Variance is large, right? That's what the implication is. Now, once I add this lambda, I'm going to introduce a small bias, but the variance is going to drop quite dramatically, right? So in this case, let's say the true value of W is 1 and 1. Okay, this is the true W, which we will never know, but because the variance is so large, every time you estimate, you get these widely varying W's. Now, if the true value is this, and I add a small lambda, what's going to happen is this variance is going to drop quite a bit. It'll introduce a small bias, but it won't matter. Now, what you're going to see is you're going to probably see 1.2, 1.5. Again, you estimated 0.8. You might see 0.9, and so on. There is going to be a bias, but the variance will drop significantly when you introduce that regularization parameter. It goes by different names. This is also called Tekanow regularization or regularization. I think there are different names for it. Yeah. Sorry, go ahead. Yeah. By non-invertible, what we mean is, determinant is close to 0, not quite 0. If it is 0, then your variance is infinity, right? Then you can't do it. Right. By non-invertible, what I meant was your determinant is very close to 0. There are some eigenvalues of X transpose X that are close to 0. So when you invert it, it's, yeah. I don't mean, when I say not invertible, I should be probably a bit more precise. I don't mean the determinant is 0, or at least there's one eigenvalue that is 0. Even if it's non-invertible, right? One eigenvalue is 0. Then you can add this lambda and make it invertible. The purpose is to reduce the variance, and the cost you're paying is the increase in bias. And this works really well. I've used it many times. Tekanow regularization, especially when you have data that are not informative enough. Right? So assume all your x's are the same, all your y's are the same. Then you can't invert that, right? When you have a non-informative data, you can do this Tekanow regularization. It's a widely used concept. Okay, so these plots here, they sort of illustrate my point about lambda and the bias, right? So here, ridge regression with different values of lambda, increasing lambda reduces model complexity, or I think what is meant is that it reduces variance, but it increases bias. As you go from here to here, and then here, you'll notice that as you keep increasing lambda, there comes a point where the bias is really, really large, right? This is not very helpful. So you might want to stick with something like this, or maybe this, right? One of those. The many benefits to using ridge regression. It penalizes square weights. It has a non-sparse solution. Okay. And it has no feature selection, gives better prediction when output variable is a function of all input features. Its regularization is often able to learn complex data patterns. Okay. So that's one type of regularization. There are other types of regularization. Has anyone here heard of compressed sensing? Compressed sensing? No. Okay. So it's an interesting concept. Have you? There are many who are electrical engineers here, right? Have you heard of Shannon's theorem of sampling? Yeah. Can you explain what it is? Yeah. Right. Okay. So does anyone know Shannon's theorem of sampling? So if you have a signal, let's say you have a sine wave, right? You have to sample this at least as fast as twice the frequency of that signal in order to. Sorry. Shannon's theorem of sampling. Yeah, it's a Nyquist criteria. Yeah, I mean, you probably know it as Nyquist criteria. So you have to sample it at least twice the frequency of this. Yeah. So I think in the early 2000s or something, there's a guy, Immanuel Candace at Stanford, and Terence Stahl. Have you heard of Terence Stahl? He's a well-known. He's considered. Perhaps the best mathematician ever. Right? He's at University of California, Los Angeles. He won Fields Medal and many other things. Very, very smart guy. He and Immanuel Candace, they came up with this idea that if you can actually sample slower than twice the frequency of your signal, and still reconstruct your signal if you're sampling randomly, right? So Shannon's theorem it assumes that you're sampling regularly, right, at regular intervals. But if you sample randomly, then you can reconstruct these signals a lot more efficiently with fewer samples. That is roughly what they came up with, and that led to something called compressed sensing. They figured out that you actually don't need to sample signals as fast as we thought we needed to in order to reconstruct them exactly. Okay. And some of that is based on one norm minimization that is used here, the one norm minimization. In the previous least squares subjective function, we had the error, the least squares error, and a 2 norm of the weight of the parameters in the objective function. Right? So you remember the difference between 1 norm and 2 norm. Right? So this is, instead of using the 2 norm of weights W, we use 1 norm of weights in lasso regression. And it turns out that when you use the 1 norm in this objective function, the W is going to be sparse, meaning when you use 2 norm, your W will have non-zero elements, most likely, in all the spaces, in all the elements of the vector W. But if you use 1 norm in your objective function, your W will have lots of zeros and some positive or some non-zero values. So 1.2, 1.5, and so. Okay. So this norm is also called sparse and enhancing norm. There are reasons for that, but the point is, if you have a model where, let's say, you don't know the exact polynomial model, the order of the polynomial model, and you randomly pick 100 features, from x to x squared to x cubed, etc. Right? And you really don't want a complex model with 100 features in them. You want something that is much smaller than that, but you don't know exactly what features to pick and how many features to pick. Right? Then if you use one norm in your objective function, what's going to happen is this one norm forces W to have many zeros in it, okay? And only a few non-zero elements, and therefore it automatically identifies the correct features that you need to include in order to get the best modeling error. Makes sense? So maybe I can write this down. So if let's say you choose y equal to some beta plus x squared all the way to 100, x to the power of 100. And I do this because I don't know what powers of x give me the best prediction for y. Now, and sorry, I should include all these w's. So W1, W2, W3, W101. Okay. Now, if you use standard least squares with regularization, where you regularize using the 2 norm of W, you will get a W that has non-zero elements everywhere. Okay. If you use 1 norm, you will get a W that is going to have a lot of zeros in it and just a few non-zero elements. Okay. In other words, let's say the non-zero elements are W3, so x squared, plus W50, that is x to the power of 49, and so on. So it automatically picks the powers that have the best predictive power for y. So that's the advantage of using W1, and it's called lasso regression. Okay. There's a geometric interpretation of why that happens. Okay, so this is similar to what I explained earlier. Lasso regression, the benefits are that it penalizes sum of absolute value of weights. It has a sparse solution. It can have multiple solutions. It has built-in feature selection, meaning it's automatically selecting the right features for your model by forcing sum of the weights to 0. It forces sum of the weights to 0, and therefore it naturally picks the weights that are appropriate for your model. And it generates models that are simple and interpretable, but cannot learn sometimes complex features. There are what are called elastic nets, elastic net regression, which tries to combine the best of ridge regression and lasso. And the idea here is you not only minimize 1 norm of W, but also 2 norm of W. Okay. So you have a combination of this. This is called an elastic net. There's no analytical solution to find W. If you have this expression, we have to use a quadratic programming algorithm. All right. What time is it? Okay, so I'll spend about 10 to 15 minutes describing Gaussian processes. I think Gaussian processes are very important from a modeling perspective. You should try that when you don't know what the model structure is. You're interested in building a non-parametric model. Gaussian processes come in very handy. One advantage of Gaussian processes is that when you build a least squares model, you get your W. You can, of course, estimate the variance on W, right? It's sort of in a way, it's an afterthought. You get your W, and that's what you use in predictions. Your W, you can estimate the variance, but it's sort of on the back burner, right? You're not using it when you use the model. Or you can use it, but it's not explicitly embedded in the model. On the other hand, with Gaussian processes, they provide a distribution for your predictions directly. So meaning you don't get y hat, you get a distribution of y hat with a mean and a variance. So in my view, that's the power of Gaussian processes. Uncertainty is automatically embedded in the model predictions. Okay, so here's just a summary of what we've done so far. We started with the linear model and then some nonlinear model. Now we're going to go to the non-parametric models, Gaussian processes. There is a lot of stuff here. Some of it will take a significant amount of time for us to derive and go through, but I'll give you a some high-level intuition into these Gaussian processes. Okay. All right. A Gaussian process is essentially a generalization of a multivariate Gaussian distribution to infinitely many variables. Okay. So what does it mean? Okay, let's say I have some function f of x that I want to approximate or build a model for. Okay, that's my function. Gaussian processes, if you imagine you split this function into infinite number of variables, okay, for different values of x. Gaussian processes essentially approximate these infinite variables using a multi-dimensional Gaussian process. So you can call these f1, f2, f3, etc. These are the values of the function at different points on the x-axis. And the Gaussian distribution of all of these values of f is going to be something like this. Mu is the mean, sigma is the variance. A Gaussian process is fully characterized by a mean function and a covariance function, and is written like this. F of x follows a Gaussian process with mean x and covariance x prime. So what does it mean? How do we interpret it, right? The way it is interpreted is, so let me write this here. F of x has this distribution. Okay? So for any given value of x, let's take x2, f of x2, which is f2 over there, it has a certain distribution. In this case, it's Gaussian or normal with mean mx1 and covariance x1, x prime. Okay, so I'm going to tell you what this function is. It's a kernel matrix. We're going to see that in a minute. Sorry, this is 1, x1. Okay, so in other words, think of it as breaking your function into small pieces, and then using this idea, you can find the variance of your function at any of those points. Okay, so this here basically tells you that the value of the function over here is a Gaussian, okay, with a certain mean and certain variance. So I'm going to skip that. The k is it's called the kernel function. It's basically the covariance between x and every other data point in your data. Okay. Some of these are probably not obvious or not clearly presented there. So this is one example of Gaussian process. The data black points denote the data. The red curve is the Gaussian process model, two-dimensional Gaussian process model. The covariance function, the kernel function, it represents covariance between different pairs of the data points that you collect. Okay. Gaussian processes. I want to, there's a, so when you have a regression problem, you want to map finite training samples to your function that predicts all possible inputs. So that's your data, that's the model. Given x star, you want to estimate y star. And then I already showed you how to learn the linear and nonlinear regression problems. You can also do the same with Gaussian process regression, where the goal is to find the mean function and the covariance function. Okay, so from using the data. Okay, I have these slides, but I'll skip those and go to this slide that explains the philosophy behind Gaussian processes. Okay. When you don't have data, you have no data, so you don't know what the function is, then there are different possible functions for your input. Okay, so I just draw a few random possible functions. Now let's say you start collecting data, so you have some values of x and the corresponding values of f of x. These crosses here denote the values of x and the corresponding values of f of x. In Gaussian processes, what happens is you assign the true value that you've measured of output to the function at the points where you have measurements. Okay. But everywhere else, you are going to use these functions, the mean and the covariance functions, to determine the uncertainty around your function. The gray patches that you see around this function are the uncertainty bands for the Gaussian process model. Okay. The Gaussian process model takes the true value where you have a measurement here. Therefore, the uncertainty is 0. This band is very narrow or 0. Where everywhere else, the gray band expands because you don't have data there. Okay. And the Gaussian processes, with those functions there, they tell you what this uncertainty band is. Okay. So I'm going to pause there, and let's do a Python exercise. If you go back to the same folder, there's a folder called regression. It has a Python notebook that you can use to try some of these algorithms. Sorry, yeah. Sorry, I did a lot of hand waving with Gaussian processes, I know. Yeah. But happy to. Yeah, great question, right? Is there anyone here who does experiments? Experiment design, so a little bit. Have you heard of Bayesian optimization? Bayesian optimization. Yeah, have you tried it? Bayesian optimization. Okay, Bayesian. See, optimization. If you know the objective function, you can precisely write it down. Then you can use gradient-based methods, right? But there are many problems where you don't know, or you don't have a functional form of the objective function. And experiment design is one area where that's very common. You don't have a functional form of the objective function. You want to minimize something, but you don't know. You want to minimize something with respect to a set of variables, but you don't have a function that relates those variables with that objective. So I'll give you an example. I work with some colleagues who do experiments. For instance, in this case, they're growing cells in a batch reaction. They want to maximize the production of cells with respect to, say, how much glucose they add and how much of feed, and they have different formulas. They add a few ingredients to grow the cells. Okay. Now I want to maximize the growth of cells, and I don't know how these ingredients impact the growth of cells because I don't have a model. All I can do is I can take those values for the ingredients, do an experiment, and find out what the cell concentration is at the end of the batch. That's all I can do. But I cannot. I don't have a function that relates these inputs to the outputs. In other words, I don't have the f of x. Right? I can find. I know I can. If you give me an x, I'll tell you what y is because I can do an experiment. But I don't know. I don't know if they are related through an equation, and what that equation is, I have no idea. Right? So, and if your goal is to maximize that f of x, how do you do that? You can't use a gradient-based approach because you don't have a function. Then Gaussian processes. In that particular context, Gaussian processes are very widely used. So what you do is you do some experiments, you collect a few y's, collect a few x's, and then you use Gaussian process to approximate the f of x. Okay, and then then once you have the Gaussian process model, you can maximize or perform optimization. That's one area where it's widely used. I think simply put, problems where you don't have a functional form of the objective function is where Gaussian processes are useful. The beauty of Gaussian processes is that they provide you the uncertainty around the function. Right? That's part of the model. The model has a mean and a covariance. For any value of x, you can get the mean and the covariance. Okay, so let's. I think our break is at 11:30. So let's quickly go through the Python notebook. We'll spend 15-20 minutes, and when we come back, I'll spend some time on reinforcement learning. Sorry.
Gordon. finish what's there. Try building a deep neural network for classification. Oh, you're doing the next Python notebook also has the So I think in the Python notebook is something called radial basis functions, RBF. Those are, okay, when you build regression models, you don't necessarily have to use y equal to w1 x1 plus w2 x2 and so on. You can have w1 some function of x1 plus w2 some function of x2, etc. Right? You can approximate any function using what are called basis functions. You can choose some special functions here. Those are called basis functions. And in the Python notebook, we are using what are called radial basis functions. Radial basis functions are essentially exponential functions. I mean, they're not seeing this. Oh, online. I'm not using this. This is just for. Yeah. Take a 15-minute break.
Time the attendance. Accuracy score. In the Python note. Is it in the Python note?
Spider or something.
Accuracy score. Yeah. Different ways of doing it. I'm not sure in this particular context. What they mean by accuracy score. This is probably something squared out. Yeah. topics to cover. You're all familiar with deep learning, neural networks, correct? I covered it a little bit in the very first lecture. We can send you back to cover it. Great. And then reinforcement. Is that a topic I know some of you have done, but not everybody. Reinforcement learning is a concept topic. And then to apply Python exercise. I have one more Python notebook that called Advanced Learning. It shows you how to do classification and regression using deep learning. Some of you have tried it already.
But it, it shows a systematic approach to do that Python node. But we have to pause at 12:45 today. We just have about an hour. Let's say we spend 20 minutes on the Python notebook. That leaves us with about 40 minutes for reinforcement learning and deep learning. Is it okay? Of course, I'm going to share all these slides. But the interesting thing is almost everything is available online. Everything I covered here, there's just some really young folks with knowledge of machine learning. They're creating amazing animations and videos online. You probably watched some of those. Right? So I do encourage you to read or watch those videos. If you want to delve deeper into any of these topics. With the limited time we have, obviously, there's only so much we can do. Oh, in person, okay, yeah. For sure, yeah, that's right. Yeah. And then, you can interact with the video. I see the concept. Okay. Right. Yeah. Hopefully, the picture that I drew yesterday, explained what PCA is. It's simply that. Right? A good background in linear algebra is useful in machine learning if that's something that if you have time you might want to work on it. Yeah. Right. No, actually, if you go to genai.ubc.ca, it's a website that we created. I co-chair a committee on the use of Gen AI in various aspects of the university. We've come up with guidelines on what is allowed. We are actually asking students to use ChatGPT. Whether it's cheating or not depends on the course. The instructor has to explicitly say, for these assignments, for these tasks, you cannot use ChatGPT, right? If that's not said, I know a lot of students are using it. I just finished teaching a course on applied machine learning. Prior to ChatGPT, at the end of the course, we have a project. We read about 50 or so project reports. And the reports used to be okay, but not great. But now it's just an absolute pleasure to read all those reports. I know everybody is using some of these tools to fine-tune their reports, right? So we're not discouraging students from using tools. It really depends on the course and what skills are we imparting to students in a particular course. If it's a course on writing English essays, then obviously we can't allow you to use ChatGPT, right? If it's a course on machine learning and you're using ChatGPT to fine-tune your reports, that's okay, right? Because I'm not assessing you on your language capabilities. That's not the skill you're trying to learn in this course, right? So that's how we're trying to use ChatGPT, but we are not using. In fact, we are encouraging students to use it. We are encouraging researchers to use ChatGPT. I myself use it quite extensively. It saves me a lot of time. Programming, yes. It's not.
With the practice, really one has to write a lot of lines of code to just memorize what will come next.
Right.
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 It saves a lot of time.
It saves an enormous amount of time for me. Okay, let's get started. I think it's about 11:48. So I'm trying to debate what to do here. Are you? I've talked about deep learning. So maybe I'll just go through neural networks very quickly in 5-10 minutes. Would you prefer that, or would you like me to just jump into reinforcement learning? Spend time there. Do you have no preference? So I'm assuming you all are familiar with neural networks, somewhat. Yeah. So maybe I can skip it, right? Okay. We'll just jump into reinforcement learning. So, sorry, let me use a different set of slides. Now, these slides include not just the standard vanilla reinforcement learning, but a few other aspects of it that we did research on. So it's a little more advanced than what you will perhaps find online with respect to reinforcement learning. How many of you have taken a course on control in your undergrad somewhere? Hoping everybody. So if you're an electrical engineer, mechanical engineer, or chemical engineer, I'm sure you've taken a course on process control or control theory. So reinforcement learning, for many decades, let's say 2-3 decades, there were two groups of researchers trying to solve very similar problems. Okay. So one group is these computer scientists working on reinforcement learning. They have an entirely different set of phrases to describe those problems in reinforcement learning. And then we have control theory. The control theory has existed for maybe 7 decades. For many years, they have worked on very similar problems, but they use different terms, different processes. Different phrases. In control theory, we have something called a controller and something called a process. In reinforcement learning, instead of a process, they have an environment, and the controller is essentially an agent. Okay. So in standard control, if you have open loop, let's say there's no controller, you pre-plan your actions. They're generally relatively simple. But the problem is when there is no feedback, your errors get compounded. Okay, so let me just go back to this. The goal behind reinforcement learning and control is you have some process or some environment that you want to control. You want to extract the behavior that you want out of this process, out of this environment. Okay. Then the way to do that is you can pre-plan your actions, which is generally very simple. But the problem is when you pre-plan your process, your actions, say something changes, then the errors compound. Right? So an example would be, let's take a simple example. Say, you're going from point A to point B. Beforehand, you decide what path you want to take, and then once you start, there's construction or some block, some some blockages and you can't go on a certain road, then you have to take a different road, right? Different path. So open loop control is like pre-planning your entire path and hoping that it works. And often, because of unknown disturbances and other things, it's not the best approach to controlling your processes. Okay, but it's relatively simple. Before you start your journey, you know exactly what plan or what path you're going to use, and therefore it's relatively simple. But the errors compound, and it's not the best way to control processes. So that's where feedback comes into play. So if you add feedback and a controller, you can online dynamically correct errors. Therefore, this approach is going to be robust and stabilizing. Okay, so this is a little bit of background on control. The problem is feedback loops often underperform. One control loop, if you just have one control loop, it's manageable. You can build a model, synthesize a controller, validate it, and then install it on a real industrial process. But what if you have hundreds of control loops for, how do you scale your algorithm? How do you go from process data to controller? And that's not clear. Okay, so we have used reinforcement learning in the context of replacing these traditional industrial controllers. So what I'm going to do is explain to you how we've used reinforcement learning in this context, and then also tell you about how reinforcement learning works, the algorithms are built, etc. So I think nearly 7 years ago, I went to Honeywell and I told them we can replace their controllers with reinforcement learning agents. What you see on the left-hand side is what typically happens in industries right now. So you have some environment, some process at the top, and then there is a controller, it's a PID or a model predictive controller or some other controller. And then you have operators and engineers who are constantly monitoring these controllers so that their performance is maintained on a continuous basis. So I went to Honeywell and I told them, okay, look, we have these nice, cool algorithms, deep neural networks and reinforcement learning. We're going to replace all your controllers with reinforcement learning and deep neural networks. And they said, we've already invested millions of dollars in our existing infrastructure. There's software, so we don't want to change our existing infrastructure. Then we came up with this alternate idea of just replacing the human in the loop with a reinforcement learning agent, which oversees the performance of existing controllers. What you see on the right-hand side is a pilot scale facility that Honeywell built for us to test some of these algorithms. Okay, so the question we asked was, can reinforcement learning help maintain these control loops? Okay, the answer, it turns out, is not very straightforward. You can leverage observed data to improve operations. If you have reinforcement learning, you can leverage observed data to improve the operations. You can, with reinforcement learning, you don't need any prior knowledge. It'll still work. You can minimize prior domain knowledge. And you can also build this automated agent that will maintain your controllers without any or much human intervention. But the challenges are there is additional algorithmic complexity. Industries already have auto-tuners. And stability during and after training is very important. In addition to that, sample efficiency of these algorithms is very important. So our goal was to balance the automation and scalability of reinforcement learning using control theoretic tools to create efficient and safe improvements. Okay. So that's the context in which I'm going to explain reinforcement learning. We're using reinforcement learning as a tool that could potentially eventually replace traditional control systems. How does reinforcement learning work? It works through an approach where it tries to maximize the reward through experience. Some of the pictures that you see are examples where reinforcement learning has been used. Now, focus on the picture, the block diagram in the right top corner. So the environments, I showed you in the previous slide, I called it a process, right? So process and control are, they are the language of control theorists, right? Whereas in reinforcement learning, a process is your environment. Okay? They mean the same thing. The controller is the RL algorithm or RL agent. Process or environment generates outputs, measurements. Those are your observations. RL algorithm uses those observations or data to take action on the environment. Okay. And how does it choose those actions? It uses something called a reward function. Okay. That's something that you have to design. You design a reward function, and then you give it to the RL agent. The reward function essentially tells the RL agent whether it's doing well or not. Okay. If it's the goal or the objective of the RL agent is to maximize the reward function. It's always working towards maximizing its reward function. In some ways, I think RL is the reason people are worried AI can become really autonomous. RL is, there's some work done in reinforcement learning in process systems engineering. So that's an example. When we first started using reinforcement learning, we realized that there are two major problems with reinforcement learning. And I'll explain what those are, and then we'll dive into what reinforcement learning is, and I'll also show you how we try to tackle those problems. And the two problems are stability. When you use reinforcement learning, in the previous picture, for instance, in this picture, you'll notice that there are these iterations happening, right? Your environment generates an observation, RL algorithm figures out what the reward was, and then it generates a new action. And you go through these iterations between the environment and the RL agent. Now, what it means is, as you're going through these iterations, your agent is trying to perturb the system, is trying to excite the system, is trying to generate new information from the system. And when it does that, you want to be sure that your closed-loop system is still going to remain stable. If you're not stable, the closed-loop system, then you're going to be in big trouble, right? Especially in the process industries. You want to make sure your closed loop is always stable. So we very quickly noticed that with RL algorithms, stability is a major problem. Okay. Do you all know what the concept of stability? Yeah. Input-output stability of the systems. No? Not. Okay. So stability, so what it means is as your agent generates actions, you want your observations to be bounded, meaning they don't exceed a certain value. The observations don't run away. An example, for instance, in a reactor, you have temperature, nuclear reactors especially, it's easy to have a runaway temperature, meaning it just keeps increasing if it's unstable. So you don't want to get into a situation where through these iterations between the agent and the environment, you have a situation where the system is unstable, meaning something is just blowing up without a bomb, and that's not good. So you want to make sure that you stay stable as you're going through this. Okay. So I'll get back to this in just a moment. Trying to see if I should do this first. Or reinforcement learning. I have a Yeah, maybe I should go in the order which my slides are. Did anyone here take advanced control courses? State space models? Are you familiar with state space models? Controllability? Okay. That's okay. We're going to go slow, and I'll try to explain these as slowly as possible. Okay. So stability is one problem. The other problem is data efficiency. Because you're going through these iterations between the environment and the agent, you have to generate a lot of data. You typically don't want to perturb the system too much, because when you perturb the system, you're probably deviating from the desired behavior. And when you deviate from the desired behavior, there's a cost associated with that. So, for instance, you're manufacturing something, and you start perturbing your system, you end up making poor quality product that you can't sell, therefore you lose money, right? So you want your systems, these agents and controllers, to minimize their interactions with the environment as they're trying to control the behavior of the system, right? So, so the two problems we notice with reinforcement learning. One is stability. We want to make sure the agent is stable. And number two, we want the agent to interact with the environment to the least extent possible. We don't want it to interact too often and disturb the system, the environment. Okay. I'm going to take you through some basic control concepts. If you have seen this before, it's going to be easy. If you've not, I'll try to provide you with some intuition as much as possible. Right. LTI stands for linear time invariant dynamics. Most systems that we deal with, at least locally, behave as linear systems, meaning the underlying dynamics of these systems are defined by a first order or a higher order linear differential equation. Now, when you have a differential equation, you can discretize it and write it in the form of those two equations. When you have a linear system, a system that's defined by linear differential equations, you can discretize the equation, differential equation, and write it in this form. This is called state space model. This is the state space model of a linear time invariant system where X represents what are called hidden states. A, B, and C are some matrices. U are the inputs to the system. You have inputs to the system. I'm going to assume in the rest of this development, inputs and outputs are scalars for simplicity. A, B, C are typically unknown. If you know A, B, and C, you know the model of your system. You've probably heard of impulse response, right? So if you have a state space model, then the impulse response from X is given by x0. You start at x0, x0 equals 0, y0 equals 0, and then you have x1, x2. You can use those recursive equations to find the value of x, the impulse response, at different time instants. Okay, so that's the impulse response. What you see here is the input to the system. So if you have a first order system and you provided this input, you're going to get this output. This output is the impulse response. Now, there are two very important concepts in control theory. They're called controllability and observability. The idea behind controllability is if I give you two states, x1 and x2, can you always find an input, a sequence of inputs u, that take you from x1 to x2? Okay. If you can, then your system is controllable. It turns out that this matrix here, C, that is made of the system matrices A, B, and C, if that matrix has full rank n, then your system is controllable. If that matrix does not have full rank, then you cannot take your system from one arbitrary state to another arbitrary state with a unique sequence of inputs. That's not possible. So controllability is a very important concept. Unless you have controllability with your system, you cannot get the behavior you're hoping for. And a dual concept to controllability is observability. If I give you the inputs U and the outputs Y, can you find the entire state sequence, X? X's are states, they are hidden, they're not measured. So the question is, if I give you Y and U, can you recover a unique X, the underlying states, a unique X? If you can, then you have a system that is observable. And this matrix here, again formed using the model matrices C and A, is called the observability matrix. And one way to check if your system is observable or not is to look at the rank of this matrix. And if the rank of this matrix is full, if it's N, then you have an observable system. Okay, so these are two important concepts in control theory: controllability and observability. Now you will recall that the impulse response is given by that expression there. It's the product of C times a to the power of n minus 1 times B. Then you can multiply the observability matrix with the controllability matrix to get this, what is called a Hankel matrix. And you notice that each row here essentially has the impulse response coefficients. Okay, those are the same. Those are the same impulse response coefficients. But if you take any row, you have the entire set of impulse response coefficients. So the product of observability and controllability matrices will give you this Hankel matrix. And I'm going to use this Hankel matrix to do something cool. So let me take a step back here and explain what I'm trying to do. So I'm going to get to reinforcement learning. But in order to do reinforcement learning, I will, I want to build a model from data, okay? And I don't want to use parametric models. I just want a data-based model that's not parametric. And to do that, I'm going to use something called Willem's fundamental lemma. Okay. So intuitively, what it is if you have an impulse, okay, so this is the impulse response, that's the input, that's the output. Now you can think of translating that impulse and generating partial impulse outputs. And you put all of these together, you get the Hankel matrix that I showed you here. So this Hankel matrix. Okay, so that picture essentially shows that each row here is obtained by moving the impulse response. Okay. So let me explain what Willem's lemma is. Sorry, this is probably a bit dense, but as long as you get the intuition, the idea, I'm going to be happy. Willem's lemma, it's a lemma that helps you go from data to models without using a parametric model. If you have a signal Z that goes from t equal to n minus 1, and you define a Hankel matrix of order L, then if you have a new trajectory, UTYT, goes from t equal to 0 to n minus 1, where U is persistently exciting, which means it has enough information in it of a certain order, L plus n, then there is a new trajectory, U bar, Y bar, if and only if there exists an alpha such that this expression is true. Okay, so what does it mean? I explained to you what Hankel matrices are. Okay. Now, you create a Hankel matrix with U, create a Hankel matrix with Y. You do an experiment, collect your U and Y, and you create these Hankel matrices. Then, any new trajectory of your system, U bar and Y bar, will satisfy this equation. Okay, so where you multiply your Hankel matrices of previously observed data with some alpha, then you get the new data set. Okay, so this idea or this lemma is used as a way to make predictions for the reinforcement learning algorithm that I'll describe in just a moment. This is a slight variant of the Willems lemma that I showed you earlier, where you create a dynamic version of the Hankel matrices. There's an entire algorithm on how to do this, but the point that I'm trying to make is if you observe some data, the blue data is the past data, you can use Willems lemma to make predictions about the future. Okay, just using data without any parametric models. Okay, now with Willems lemma, we are able to characterize the system, meaning we have a model for the system. Now, how do we drive its behavior, right? Here we use, has anyone heard of Euler-Kucera parameterization of controllers? Okay, so it's a way of characterizing all stabilizing controllers, okay? So what is a stabilizing controller? So let's say if you're given a controller and you have to find whether it's stabilizing or not, a controller K, it's not easy. On the other hand, Euler-Kucera parameterization allows you to build a class of, characterize a class of stabilizing systems. Okay, so I'm going to explain that with very simple graphics. The P here represents your system or process. Let's say that's the output of your system. And Q is some other stable dynamic system. So as long as the output of this stable dynamic system is bounded, the output of your process is also going to be bounded. In other words, if I put this Q in front of P, together, they're both going to be stable as long as your P is stable and this Q is stable. And this idea is used in parameterizing all stable controllers using Euler-Kucera parameterization. Okay, so if you have a P that's stable, Q that's also stable, then what you can do is the following. Oops. Sorry, there's too much animation here. All right. So if this is stable, this is any Q in front of it will also be stable. So you can use that idea to characterize all stable controllers. Okay, so these two are equivalent. Here, if you look at this, you're taking this output and you're subtracting it from the controller, and inside the controller, you're adding the output of P, right? So you add and subtract, it's the same thing, so you get that. So this is a different way of showing the same thing. And now you have this controller that's going to be stable as long as this whole thing is going to be stable as long as you pick a Q that is stable. In that way, we have characterized all controllers that are going to be stable as long as your Q is stable. Okay, so far I've told you there's this Willems lemma that gives you a model. Then I've also explained how you can characterize all stabilizing controllers. The last ingredient to what we're trying to do here is reinforcement learning. Okay, so and I'm going to spend a little bit of time here to explain how reinforcement learning works. You have so the environment or the process. Okay, the process generates some states, st plus 1. So this is In reinforcement learning, we use S. In control, we use X. They are the same states. Okay, so in control literature, typically you'll see people using X to denote state. In reinforcement learning, you'll see them using S to denote state. Okay, so the environment generates a state, and we also use the measurements from the environment to define a reward. Okay, a reward is your R. And the state and the reward value are given to the agent. We'll talk about what's in the agent in just a moment. The agent then determines what action it's going to take on the environment. And the way the agent is going to decide the action is through something called policy. It's policy pi. So pi is the policy. Policy in the control language is the control algorithm. It's same as or it's similar to control algorithm. And you go through these iterations. Agent takes an action, environment generates a state, and a value for the reward. Okay? And those two are sent back to the agent. The agent then updates its policy based on how it has performed with the previous action, and potentially generates a new policy which generates a new action, which is again applied on the environment. And you repeat these iterations again and again until the goal of your agent is to maximize its reward. Okay, it just maximize it to the extent possible. Now, if I compare this to control, in control, what is your objective? Typically, your objective is to minimize the control error, right? So, what is a potential reward function in the context of control for an RL agent? What can you think of a potential reward function? In control, you want to minimize the control error. So what is here? You're trying to maximize. Your agent's goal is to maximize an objective function or a reward. Can you think of a way to define a reward function? Error? But you don't want to maximize error, right? So negative error square, let's say, right? So negative error square could be is one potential reward function if you're using reinforcement learning. Now, the reward that you get is averaged using this function here, okay. And that's called the value function. It gives you the value of the rewards all the way into the future. You want to maximize the total value. And the goal of the agent is to find the best policy, best pi that maximizes that accrued reward. Your goal is not to maximize your reward right now. You want to really maximize the overall reward, right? You might lose now to gain later. You don't necessarily want. I think there are different approaches, but the real goal is to maximize the overall accrued reward. Okay, so if you, in the context of, let's say, chess, say you're playing a match, your goal is to win, but you might want to sacrifice a piece right now for an advantage later. Right? So, which means you really want to maximize the accrued returns, and that V is a measure of that accrued result. Okay. It's called return. This is the current return. This is the current return you're expected to get. This is the return you're expected to get in the future. And it turns out that this value function satisfies a certain recursive equation. I don't want to delve into the complexities of this in the limited time we have. But the point I'm trying to make is there's a certain recursive equation that this value function satisfies that you have to solve in order to estimate the policies. Okay. I want to show you a particular structure of reinforcement learning that is, let me use a couple of other figures here. So the V is the value function that I showed you in the other slide. Typically, what happens is you find a policy, then you update your V, then you find a new policy, you update your V, you find your new policy, and you keep doing that until your V and the policy converge. Okay. I want to show you a picture. I hope I have it here. So it's a critique. There's a particular structure of reinforcement learning that is very popular. It is called this one. And it's the same picture that I have in the other slide. Perhaps a little less busy, so easy to follow. There are two inherent concepts in reinforcement learning that you should be familiar with. One is the exploration process that allows the agent to perturb the process and learn its dynamic behavior. Right. So what I showed you earlier, the value function, the reward, etc., that's the math behind. But this gives you a high-level intuition into how these reinforcement learning algorithms work. The math behind generates actions that perturb the system or explore the system. Right? So let's say, as an example, say you are learning to drive a car, right? It's the very first time. You are going to perhaps make exaggerated steering moves or exaggerated moves on the brake or the gas pedal, right? Because you're still trying to learn. So when you do that, you try to steer in different directions and sort of learn by how much your car turns. So that is exploration, right? So you're trying to explore. And the agent automatically, using some of the equations that I showed you earlier, automatically generates those perturbation signals. So and that process is called exploration. So when it perturbs, it generates the right data. If I go back to the car analogy, you make a certain move with the steering, you learn how much your car turned. The next time, if it's too much, you're going to make a smaller move, right? So that's exactly how reinforcement learning agents work. They explore first. They try to generate data. And using that data, they learn the behavior and start getting better. Now, there is a particular variant of reinforcement learning that is very popular, and that's why I wanted to bring up this picture. It's called actor critique approach. Okay? And the way it works is your environment is going to generate a reward. The reward is used in this value function V, which I showed you in the other slide. And that's used to approximate, the value function is used to critique the previous action, meaning it tells you whether the previous action taken by the agent is good or bad. Okay? And that information is essential to update your actor. Okay? So if it's bad, you update your actor in a certain way. If it's good, you update your actor in a different way. Okay? So these two form your agent, actor, critique. They're both in one box. They're both together called reinforcement learning agent. Right? At the end of the day, the critique and the actor which has the policy, they're both functions, right? Some functions. Now, it turns out that there are many different ways in which you can approximate these functions. You can, you can use verbally basis functions. You can use a variety of approximations for these functions. And when you use deep neural networks to approximate the critique and the actor, you have what is called deep reinforcement learning. Okay. Okay, so that is reinforcement learning, and when you put the Willem's lemma that generates this model, the stable model, and then Euler-Kucera parameter. Sorry, this gives you the Willem's lemma gives you the model here. Euler-Kucera parameterization Q, make sure that the closed loop is stable, and then we use the learning algorithm to control the overall process. Okay. So this approach, this is something that we came up with. Some of these ideas are patented. We try to decouple learning and stability. RL is layered on top of all the stable behavior. Okay. Reinforcement learning is really tuning this Q, the controller, or Euler-Kucera parameter. Okay, there's some examples here. I think I'd briefly shown this earlier, but I'll explain what this is. That was my student, Nathan Lawrence. He's now a postdoc at Berkeley. Vancouver, University of British Columbia is on that corner. He used to drive to Honeywell in North Vancouver. This is a pilot scale plant that they designed and built for us. He was controlling this plant using the algorithms that I mentioned below. Not exactly the same algorithms, but different variants of those algorithms. Honeywell also developed an interface for us to interact with this tank. Okay. I believe this data is from that experiment. You can see the set point changes and the tracking performance of the RL agent. And it turns out, as I mentioned earlier, there are a lot of off-the-shelf auto tuners. For instance, Honeywell auto tuner. This is some information from a standard Honeywell auto tuner. The question we started asking was, is reinforcement learning algorithm that we developed, is it as good as Honeywell auto tuner? It turns out that in the experiment that Nathan did, Honeywell auto tuners took about 5 minutes to tune a controller. His algorithm took 50 minutes. So that did not make sense. We wanted to figure out a way to speed up these reinforcement learning algorithms. He compared those algorithms with a wide range of the reinforcement learning algorithm that he developed with a wide range of other algorithms that are in the market. SIMC is an algorithm by somebody, Skogestad, Sigurd Skogestad at NTNU. So we compared deep reinforcement learning with different performance metrics against AccuTune 3 is a Honeywell controller. SIMC is Skogestad's IMC controller. Our algorithm worked better with certain metrics, but the challenge was it just took too much time, right? So if it takes 50 minutes when a Honeywell auto tuner can do that in 5 minutes, it's not very helpful. Okay, RL plus PID. We have also used reinforcement learning to tune PID controllers. So I'll skip that, and I'll just go to one explain a couple of other things using what is called meta reinforcement learning. Surendra and I, we have to leave at 12:45, but I'll give you the advanced learning Python notebook. You can spend 15, 20 minutes on that. Okay. It doesn't have, unfortunately, code for reinforcement learning. You can get it online. There are lots of controllers. As I mentioned yesterday, Open Gym. So if you have time today, what I suggest is, I don't have this code, but I'm sure you're smart enough to ask Gemini to build it. If you go to Open Gym, there is a lunar lander. Okay? It's a vehicle that's supposed to land on moon. That's the simulator. That's the environment. In Open Gym, you'll find a lot of environments. I talked about environments, right? In Open Gym, you'll find a lot of open source environments. Okay? The lunar lander is one of those environments. Take lunar lander and use reinforcement learning to land it. The land on top of moon, they have 2 flags. Your goal is to land that lunar lander between those 2 flags. Okay? You'll find code online for reinforcement learning. You can probably use that and figure out how to land it between the 2 flags. So the last topic of interest for us when we were working with reinforcement learning was sample efficiency. As I mentioned, if Honeywell auto tuners are tuning controllers in 5 minutes, and my reinforcement learning algorithm takes 50 minutes, that's not very helpful, right? So it's not going to be competitive. So we wanted to figure out how to improve the sample efficiency of reinforcement learning. And to do that, we use a tool called meta reinforcement learning. Okay. I've given this example. Did I give you the example of? I think I gave you the example of balanced bikes, right, on the first day. You remember? Yeah. So that's meta learning actually. So in meta reinforcement learning, what you do is you take your RL agent, you train it offline on a wide range of environments. Okay? So let's say you think your true environment is a first order differential system. Then in simulations, you take a wide range of first order systems and you train your RL agent to work on all of them. Okay? Your RL agent is trained on, say, 1 million offline systems. Anything you do offline is not expensive because online, I mentioned how these iterations between agent and environment can cost you because you're perturbing the process, and that's cost, right? But offline, if you have a model, you can do those perturbations any number of times without any problem, right? Without any incurring any cost. So in MetaRL, what you do is you come up with a large number of models and train your agent on all of those models. You train your agent to work on all of those models. And in the process of training it, your RL agent encodes the information about each of the environments that you've trained on using a hidden variable called Z. So what you see here is Z is a hidden variable that in a way captures the information about each and every system that you have trained your RL on offline. Okay. And then I don't want to sort of delve into the technical details here, but the idea is you train it on multiple systems and you take it online. When you take it online, it very quickly realizes it goes back to its memory. Think of it as RL going back and searching in its memory to see if it has been trained on a system like that. Okay. And if it has been trained on a system like that, then it has the memory of how to control it, right? So it immediately implements a policy that is relevant to the system that it's currently seeing. So I'll show you some examples here. At the top, right in the top right-hand corner, you see, maybe I should zoom in. Let's see if I can zoom in. Right. The solid black line is the set point. The dotted line, the green line is the output. So now because this RL agent was trained offline on a wide range of systems, if your system changes, let's say your time constant changes or the gain changes, something happens to your system and it's behaving differently, and because your RL algorithm was trained on multiple offline models, it can very quickly adapt. Okay, so that's the adaptation part. I think that somewhere over here we changed the system. RL agent very quickly learned and started controlling the new system. And this is another interesting example where the solid line shows the set point. The purple line is what a typical PID or other controllers that are not tuned would do when you change the system. And then the green line shows the response of our meta reinforcement learning algorithm. Right? Even if you change the system, underlying system, it automatically learns what you have and starts adjusting its policies appropriately. Okay, I think I showed you some of these examples in my very first lecture. So I know I apologize. I know I went through a little fast. There's a lot of material there, but my hope is that you'll go away with some intuition into how these algorithms work. If you really want to understand the nitty-gritty mathematical details, you will have to spend many hours reading reinforcement learning. Hopefully you understand what reinforcement learning is and how it works broadly at a high level, and I've shown you some applications. Hopefully you've also seen the parallels between control, which you may have studied in your undergrad, and reinforcement learning. Reinforcement learning is used in large language models as well. They use a variant of it called reinforcement learning with the human feedback. Okay. It's widely used in robotics and a variety of other areas. It's a very popular tool for solving optimization, control problems under uncertainty. The main person, or one of the main people behind reinforcement learning is Rick Sutton. He's at University of Alberta. He received a Turing Prize 3 weeks ago, I think 3 or 4 weeks ago. Turing Prize is considered the Nobel Prize in computer science for his work on reinforcement learning. All right, I'm going to pause there because I have to run somewhere else with Surinder. If you can, I know we have time until 1 o'clock, so it's about 15, 20 minutes. There is one more Python notebook, the last Python notebook. It's called Advanced Learning. You can just open it. It has a code for classification using deep learning and regression using deep learning. And the other exercise, take-home exercise for you is to use OpenGym, download the code for the lunar lander, and then create a reinforcement learning controller to land it between the two flagpoles. Okay, so you'll find it. Yeah. Mm-hmm. Yeah, it's a control. Okay, so maybe I've emphasized too much of control. It's used for decision making. Okay, so control is a form of decision making, right? So at every time instant, you have to decide what input to apply to the environment. Now let's take the game of chess, right? There again, you can use reinforcement learning to play. The bots that are used, they use, I think, some form of reinforcement learning. So if you're playing chess, let's say I'm the bot, the reinforcement learning agent, and I'm playing with you, then at every move, what I have to do is I have to calculate all your possible moves into the future, and then I have to calculate my reward, right? So my reward 1,000 moves from now. I mean, chess games don't last 1,000 moves typically. Now I can say, so there are different possibilities, different moves that you can make. Now as an agent, what I will do is, if I make this move, and then there are different possible moves that you can make, what is the end result? Am I going to win? Am I going to lose? Right? That sort of gives me one reward. Then you have to calculate rewards for all possibility. It uses that information to decide what the best next optimal move is, so that on average, my reward is going to be positive. I'm not going to lose the game. Right? And then you repeat this process after every move. So it's used in other applications. I think the way I think of it is it's a tool to make optimal decisions. Okay, under uncertainty. Okay. When there's a lot of uncertainty, it'll let you take optimal decisions. If you read the theory on reinforcement learning, there are some, you cannot apply it to every problem. There has to be an underlying what is called a Markov decision process, so, which is basically the state space model there. That's a Markov decision process. So there's some caveats, some theoretical constraints that you have to meet in order to apply reinforcement learning. But overall, you can use it for decision making, in optimal decision making. That's the idea. Yeah, for sure. Rick Sutton. Rick Sutton's book is a very reinforcement learning by Rick Sutton. All right. Yeah, so I can write it. His book is it's actually a very thick book. It probably has 1,500 pages in it. But if you want to learn the theory of reinforcement learning, I highly encourage lectures by David Silver. If you search David Silver RL on Google, you'll find his entire set of lectures. Sorry? Yeah. Machine learning books, and yeah. So for classical machine learning, I recommend statistical learning. By Trevor Hasty and Rob Tibshirani. Okay, so Trevor Hasty is, I think, the first author or one of their students. But if you search Trevor Hasty statistical learning, you'll find all his books. So in those books, you'll learn the classical stuff: least squares, PCA, PLS, and classical classification methods, etc. Not deep learning and those advanced learning. If you want to learn about advanced learning tools like deep learning, then the go-to books are Ian Goodfellow. His textbook is called Deep Learning. This is also available online completely. You can't download it, but you can view it online. The other book, recently it came out, is by Christopher Bishop. I think that's also called Deep Learning. Yeah, I mean, there's another book called Machine Learning by Kevin Murphy that is that focuses on Bayesian perspective of machine learning. And a lot of problems in machine learning and in statistics, you can solve them using optimization or using Bayesian statistics, where there is no optimization really. You just you find probability distributions. Okay. When you use optimization, you get point estimates for models. When you use Bayesian inference, you get distributions. So you can either get, when you do parameter estimation, you can either get a theta, or you can get a distribution of theta, density function of theta. With Bayesian approaches, you get a density function. With optimization approaches, you get a point estimate. So Kevin Murphy's book, he says he approaches machine learning from Bayesian perspective. These are substandard textbooks. All right. Thank you. I think we have to run to a different place. I'll be back here at 2:15. We'll spend half an hour or so talking about attention and transformers. Okay. Oh, we all have to go. Oh, okay.
Photo session, we have all that.
But right now they can work on the Python. Okay.
Please come in front of the. The stairs is there.
So today, if possible, 1 o'clock, we just visit there. If possible, today we'll take the photograph or tomorrow during the day. Today you are not to invited to take your lunch in guest house.